Hello, in this video I'm going to say a little bit about entropy, which is a very important idea in thermodynamics, but also one which tends to confuse people. So the first thing that I see that confuses people, particularly if they're studying more than one science before they head off to university, is they get entropy mixed up with enthalpy. So enthalpy is a very important idea in chemistry, less so in physics, but they sound quite similar and they both involve energy in some fashion. So enthalpy, for those who have studied some chemistry, is, we quite often look at it when you're looking at chemical reactions. So you might add a couple of things together, a couple of molecules, say, might react in some fashion in order to produce a couple of different products. And we can look at, well, how much energy is required to create molecule A from its constituent parts. So that's going to be the enthalpy of A. The same for B. We can then see, well, how much enthalpy have we got when we start off? We can do the same for C and D, say how much enthalpy we've got after the reaction. You can then compare these and say, well, if C and D have got lower enthalpy than A and B, then we've got an exothermic reaction where you've got an energy release. And if C and D have got higher enthalpy than A and B, then you need to put some energy in. We got an endothermic reaction, and you need to put energy in order to get the reaction to take place. So enthalpy is, we're normally looking at it in chemistry at a very local level, a handful of molecules or such like, and seeing those individual specific energy changes that might be taking place during a chemical reaction. Now, entropy also involves energy, but it's at a much larger scale. We're not just looking at a handful of molecules here. We're looking at huge systems of atoms, molecules, and we're looking at something different about the system there than we are just in these chemical reactions. So that brings me on to the first thing when looking at entropy proper that tends to confuse people is a lot of people will go to a textbook or a website and they'll see that entropy is described as being a measure of disorder of a system. Now, I don't think that's a particularly helpful place to start when you're looking at entropy. I think a better place to start is to go back to energy again and say that it is a measure of energy dispersal in a system. Now, I mean, we know more about energy. It's easier to understand what's going on, and we know what dispersal means. So this is how spread out the energy is in a particular system. So if we've got energy where a system, where the energy is concentrated in a particular location. So let's say we've got ourselves a battery and we want to plug that into our clock and power our clock. We have got a concentration of energy here. So the energy isn't dispersed. We could say the same if we've got some coal or some oil or some gas, or if we've got our uranium that we're putting in our nuclear reactor, or if we've got a water wheel that we're using to drive our millstones to grind our corn. We've got a concentration of gravitational potential energy in the water that's up the mountain, and then it's coming down through the water wheel. So in all of these cases, we've got a concentration of energy. When we then perform work, which is the transfer of energy from one location to another, if you remember back to our discussions on work in previous videos, we're then moving this energy around and we're going to be dispersing it. Now, if you've got a perfectly efficient process, we can have one energy store, we can do some work, and we can transfer all of that energy to one other energy store. So we've moved from one location to another location. If we're 100% efficient, then happy days. We've still got this concentration of energy kicking around, which we might still be able to use. But by and large, when we're doing work, we're not 100% efficient, and we're spreading this energy around into lots of different locations. So we're now spreading it about. We're getting energy dispersal going on here. So we have moved from low entropy because we've got a low energy dispersal. We've got a concentration of energy here, so we've got low entropy, and then we're moving to high entropy because we've done something useful with the energy that we had concentrated in one place. We've ground our corn, we've powered our clock, we've got our power station going, and now we've powered the steam in the turbines, and we're off spreading our electricity around. So we're moving from low entropy to high entropy because we're spreading the energy out. I mean, this brings us back to this idea of disorder. This is all very ordered, isn't it? We've got a nice bit of order in our battery. We've got a nice concentration of water at the top of the hill. We've got little clumps of fuel in our lumps of coal. So we've got a nice bit of order there. But then as we use it, the coal disintegrates, it gets used up, it all spreads out. We've got the energies now being spread out. So everything's just turning into this sort of chaos, which is what they're talking about in this disorder. The same as the water's all coming down the mountain, and it just ends up in the big mass of water that we've got in the oceans. That's where all the water's heading to, and everything's just disordered. We've just got this big load of lower energy concentration water in the ocean. It's just chaos going on there. So that's what they mean when we're talking about this measure of disorder. So the more disordered something is, the higher the entropy is, the lower the concentration of energy, or at least the useful energy that we can use. So that's all of that. And this links into the second law of thermodynamics. So in our second law of thermodynamics, this is where it is saying that entropy increases. So if we're looking at a system over time, entropy is not going to be reducing, it's going to be going up. So that's the tendency. Now you can get variations for a number of reasons, but the trend has got to be upwards. Now let's get on to these variations then, because this is another thing that can be confusing as to what's happening. Now, some of these variations might just be short-term probability-based variations. So if you've got a gas, so gas by and large, you've got all of your particles just dotted around at random. You've got energy dispersal. If the gas is in equilibrium, everything's got the same temperature everywhere in the gas. Your energy is dispersed as much as it can be. You've got high entropy and you've got high disorder, but everything's moving around at random. You might get very short-term fluctuations where you get little concentrations in particular areas because there just happens to be a randomness that moves more of the gas particles into one area of the volume of the gas than another. So you can get these very short-term fluctuations, but overall we've got our entropy is going up, or if it's in total equilibrium, we're just sort of keeping this fairly flat entropy. It's not changing very much. So and this is what it's saying in the law of thermodynamics, second law of thermodynamics, that you're either staying equal or increasing on your entropy. But then what is happening then if we are creating more energy sources, or more fuel sources, really, the more of these concentrations of energy? Our battery powers down, as it does on our phone, and then we recharge it. Well, aren't we creating order there? Aren't we concentrating our energy? Aren't we decreasing our entropy? And yes, well, we are for the battery. That's great. So in this case, the battery has gone from having low entropy. We've then used it up. It's gone to high entropy. We recharge it. It goes back to low entropy again. So wonderful. We've now decreased the entropy of the battery. But in order to do that, we've performed work somewhere else. We have to use another energy source, another concentration of energy. We plug our phone into the wall. We plug it into the mains. So we're using a concentration of energy from somewhere else. So the entropy of the battery may have decreased, But somewhere else, there's going to be another system which has gone from low entropy to high entropy, because we've used that concentration here at the low entropy in order to do the work that recharges the battery. So if you then include that whole system of saying the battery plus the mains that we've plugged the charger into, then overall our entropy would have increased. So you have to look at the whole picture when it comes to entropy, and this is how you end up on these really big systems. We're not looking at something really small and localized like we are with enthalpy. We're looking at something massive. You think of what's going on with the Earth. A large part of the fact that we can keep on doing stuff is because we've got this continual supply of energy coming in from the sun. So the entropy of the sun is increasing, but it's allowing us to decrease entropy in certain situations on the Earth because we're getting an energy supply that we can use in order to do work. So the sun is giving us that ability to do work, which means we can locally lower our entropy, but the entropy of the sun is going up. So again, that is a big system that's going on. Right, so two more things I want to say then about with this second law of thermodynamics. Right, one thing that is really, really interesting about this is we've now got what's usually called an arrow of time going on here. All the stuff that we've looked at up until now, when we were going through classical mechanics, whether we're doing optics, whether we're doing particle physics, all of this stuff, it doesn't really matter if we're going forwards or backwards in time. We look at a projectile, we can take our projectile and we work out the path of it. Great, that's going forwards in time. But if we'd started at the other end and gone backwards in time, then we get exactly the same route, exactly the same path, exactly the same results. We saw this when we were looking at our particle physics with Feynman diagrams. We can start looking at particles going forwards in time or backwards in time, and whether you've got matter or antimatter, and you end up getting the same outcomes. This is different. We've now got something which is saying, well, as time marches on, entropy is increasing. You can't start going backwards. You can't start saying, oh, well, if we reverse the arrow of time and start going into the past, everything behaves exactly the same way. We can't tell the difference. Well, we can, because the entropy has to be either staying the same or increasing as we go forward in time. So this is a real difference between the past and the future in a way that we haven't seen in the other parts of physics that we've been looking at. So that is very important. It's driving the processes, as I say, that go on in the world. We can look at pretty much everything that happens in the universe, if we want to, as being energy spreading out. This is what energy tends to do. If you've got a concentration of energy in a particular place, it will spread out. That's how the universe works. And it leads then to this idea of heat death. And this is what scientists talk about as being the end fate of the universe. That if every time you've got a concentration of energy, that will tend to be dispersed, and the entropy is always increasing, and you can't do anything to reverse this, because if you take the universe as being the biggest possible system that we can look at, well, the entropy of the whole universe must be increasing over time. So eventually you're going to get to a state where the universe has just ended up in equilibrium. All of the energy is spread out. There's no more spreading out of the energy that you can do. It is totally dispersed everywhere. Everywhere is in thermal equilibrium, and there's just nothing left. You can't do any more work. There's no more useful energy left in the universe to do work. And so when I say useful energy, it's energy that can do work. There'll still be energy there. It's just all the energy will be spread out. There's no difference from one place to another. So you'll have some energy, but it's the same energy as you've got there and in there and there and there. So what are you going to do? You can't affect any of these other things. Everything's interacting in exactly the same way. The push and the pull is the same everywhere. You can't do any more work. Well, that's just the end of everything then. If you can't do any more work, everything's come to a stop, and that's the end of the universe. So that's the idea between heat death, that if we've got a universe that just keeps on expanding forever, there's either not enough mass in it, or there's enough dark energy to just keep the expansion of the universe going, then that's the outcome that seems likely, according to the second law of thermodynamics, that we just end up with, well, yeah, there's just bland, dispersed nothingness. So on that cheery note, which admittedly will take a long time to get to, we don't have to worry about this in the short term, but on that cheery note, I will leave that there for entropy. A very, very important idea. So yeah, make sure you've got that clear in your mind as to what it means.